So, welcome back to physiology, and we're going to talk about active transport in terms of how it applies to the excitable tissues. So, the role of energy in active transport. So, there's a few rules that all of everything needs to really follow. I was going to say all of science, but that doesn't apply. It's everything needs to follow, and they're called the laws of thermodynamics. Thermodynamics is how energy gets used. And one of the things that allows a lot of things to happen is what we call free energy. And when you have the motion of particles from high concentration to low concentration, or diffusion, the energy to do that comes from this magical stuff that we call free energy. The catch is free energy has to always go down. You don't get to add in free energy. So that's what we call the second law of thermodynamics. And turns out the second law of thermodynamics will dictate if certain processes are allowed or if they're not allowed. So what we always have to do is we have to ensure that whatever is happening follows the second law of thermodynamics. So what could that be like? It could be like moving things from a low concentration to a high concentration. That doesn't follow the second law of thermodynamics, so we need to have a way to fix it. The way that they fix it, at least in our bodies, is they do something called a coupling reaction, where we take something that is not going to happen, you have to add in energy so it's not going to occur, and we pair it up with something that doesn't use up energy. It actually, or doesn't require additional energy. It gives away energy. So comparing the two, so doing both at the exact same time, if you have something that needs 5 joules of energy, but you pair it up with something that gives away 10 joules of energy, the overall result is something that we would call favorable. The thing that we typically use when we try and make reactions favorable is we take this molecule that we call ATP, adenosine triphosphate, and we break it apart. When we break it apart, the result is we have energy released, and now the body is free to do stuff that normally would be impossible. ATP is, in a sense, the battery that we use to power whatever we need to power. The thing that requires ATP, because it's not normal, is active transport. Active transport is when we stockpile stuff. We move against a gradient. We're concentrating stuff. And that will always require some type of membrane protein and a membrane, a barrier that prevents whatever we moved from moving on back. The most famous example of these proteins is what we call the sodium-potassium pump. And the sodium-potassium pump utilizes ATP to move sodium ions out of the cell into what we would call the extracellular fluid, and moves potassium ions into the cell into what we would call the intracellular fluid. What does that look like? Excellent question. Looks something like this. So we have our protein pump. Sodium ions will bind. ATP will bind and break apart. It breaking apart will actually force this protein, the pump, to change its shape, which will allow the sodium ions to leave. In the extracellular fluid, you also have some potassium ions, and those will come and they will bind. We get rid of that last little piece, that phosphate, that P, that releases just enough energy to change the shape once again so that the potassium ions can leave into the intracellular space. And now we're free to do this all over again. Sodium ions from the intracellular space will bind. We use ATP, snap, change the shape of the pump. Sodium ions go into the extracellular space. Potassium ions from the extracellular space will bind. We remove the last phosphate, changes the shape yet again. Potassium ions are allowed on in. The result is we get a concentration gradient. We're building up differences in where we're hiding stuff. And the reason why we care about that is we can make use of it. Because basically we're setting up a situation that we can utilize, much like how making a dam builds up the water level so that we can then have the water pour down some generators, and now we have electricity. We're doing the exact same thing here, just we're using molecules instead of or little itty bitty atoms and ions instead of using water.